Hi, I'm Stefan Muller, and I'm presenting our paper, Modeling and Analyzing Evaluation Cost of CUDA Kernels. First of all, if you're not familiar with CUDA, it's a framework developed by NVIDIA for general-purpose programming on GPUs, and it's gained popularity lately because many machine learning frameworks use it as a backend to do training on GPUs. It's also used for many high-performance computing applications, including, recently, modeling the virus that causes COVID-19. CUDA's execution model is massively parallel and executes on many threads to take advantage of the hardware parallelism of GPUs. Because there are so many threads, CUDA divides them into a hierarchy. Threads are organized into blocks, and all of the blocks form what's called a grid. The structure of memory mirrors this structure. Each thread has a local memory that stores per thread values of local variables. Each block shares a larger shared memory, and all threads have access to a still larger global memory. As you can imagine, memory latency is higher for shared memory than for local memory, and even higher for global memory. CUDA is an extension of C, in which designated functions called kernels run in parallel on the GPU. Because of the nature of GPUs, CUDA has an unusual execution model. Groups of 32 threads called warps execute the same instruction in lockstep, but on different copies of local variables. Each thread has access to its own thread ID, so for example, a kernel can execute the instruction increment x by TID, starting with x equals 0, and end up with different values for x. CUDA's execution model leads to some non-intuitive performance properties. For example, consider a warp executing a conditional whose condition results in true for odd threads and false for even threads. Threads in a warp take different control paths, leading to what's called a warp divergence. Because the threads in the warp have to execute in lockstep, the GPU has to disable the even threads, run the if branch, then switch which threads are enabled, and execute the else branch. This results in a more sequential execution than expected. CUDA has other performance drawbacks too, largely related to its memory model. When a warp accesses global memory, the system pulls in several words at a time from memory. So if memory accesses within a warp are close together, fewer reads are necessary. If accesses are farther apart, more individual chunks, which are called sectors, need to be read sequentially, resulting in more latency. And in the worst case, a warp may need to read 32 separate sectors. So this means that spatial locality is good for memory performance, which is not terribly surprising for systems programmers because it's good for cache performance too. So they're used to programming this way. Shared memory is a little more counterintuitive. Shared memory is divided into 32 banks that can be accessed concurrently. So for example, if threads read from consecutive array elements, all the reads are performed at once. On the other hand, if all the threads access the same bank, the reads have to be sequentialized, resulting in a slowdown due to memory latency. Because some of these performance properties are a little counterintuitive and specific to CUDA, we'd like to be able to give programmers feedback on the performance properties of their kernels, taking important bottlenecks like warp divergences and bank conflicts into account. In this paper, we developed tools for reasoning about and predicting the cost in an abstract resource metric of executing a CUDA kernel, focusing on the three bottlenecks I motivated. Our contributions include a cost semantics that models the execution of CUDA kernels on a GPU, together with the execution cost in an abstract resource metric. We've also developed a quantitative for logic that can be used to statically reason about the cost of executing kernels. Meta theorems about the cost semantics and the logic, including the correspondence between the two, are formalized in Coq. We've implemented and evaluated all of this in a prototype analysis tool called CUDA, which automatically derives bounds for the performance of the kernels. All of the above focuses on a single warp for simplicity. At the end of the paper, we discuss how to compose results to build up to full programs by using results from thread-level parallelism theory, and I'll touch on that at the end of the talk. In general, a cost semantics for a language defines the meaning of programs and the cost of evaluating them without going into details on evaluation order or the evaluation procedure. As such, we typically use a big step semantics for them. I won't talk too much about the cost semantics here because it's not particularly surprising. There are separate judgments for executing expressions, which are pure, and statements which may have memory effects. Both are parameterized by a set of active threads. Remember, some threads might be disabled, and a resource metric. The resource metric specifies rational number costs for each operation that might be encountered, such as a memory load or a function call. Both depend on the store, and statements may also modify the store. Expressions return a family of values, one per thread, and both return the cost of evaluation in the provided resource metric. As an example, I'll show the rules for if statements. There are 3 rules. 2 are on this slide, and 1 is very similar. If the expression evaluates to true for all threads, then we only execute S1, and we add up the cost of evaluating the expression with the cost of evaluating the statement, plus the cost of an if statement, which we get from the resource metric M. That's just a constant cost of executing any if statement. The rule for when all threads return false is similar. Otherwise, we split the threads into the ones that return true and the ones that return false. We execute S1 and S2 with the appropriate sets of threads and add up all the costs. We also add on an additional cost associated with threads diverging. This accounts for the cost of enabling and disabling threads in hardware, which is non-trivial. One other thing to mention about resource metrics is that for some operations, the cost is parameterized by an additional integer. For global memory reads and writes, this is the number of sectors accessed. And for shared memory reads and writes, it reflects the number of bank conflicts. Now I'll talk about the program logic we use for reasoning about cost, which is based on a quantitative program logic for C-like languages. Normally, the pre and post conditions of 4 triples capture just the logical conditions before and after execution of the statement. We now extend them to also include a potential function, which is a function from a state to a non-negative rational number. This works very much like the physicist method of amortized analysis. The potential is used to pay for the costs of operations, and so the initial potential needed bounds the cost. Potential function should have the property that if S evaluates, then the cost of evaluating S is less than the difference in potential between the before state and the after state. I'll go through if as an example. The tick command in both branches pays a specified cost, so tick 1, tick 2, cost 1 and 2 respectively. If we start out knowing P as a logical condition, we can evaluate the if branch assuming that P is true, and also assuming E is true. And we can assume the else branch assuming that E is false. Now for the quantitative part. We need to subtract off enough potential to evaluate the conditional. In this example, the condition itself has no cost. In the general case, we need to pay to evaluate the conditional expression also. We evaluate both branches with Q plus 2, which is the initial potential minus the cost of the if. In both branches, the tick costs at most 2, so we have potential Q left over at the end. Note that we actually have more potential left over in the if branch, but we can use weakening to throw away potential. So what's the good of having Q potential left over at the end? This if statement will probably be sequenced together with another statement, and leftover potential can be threaded through to the next statement in sequence. But what do the potential functions look like for CUDA? I've said that they're functions of state, but remember that in CUDA, a state includes a value of each local variable for each thread, and there are potentially thousands of threads, so tracking all of the state just wouldn't scale. Instead, we rely on an observation about most CUDA kernels. They typically have 2 kinds of variables. Some variables carry data through a program and tend to have different values in every thread since each thread operates on different data. Other variables, though, like loop indices and parameters to the kernel, tend to be the same across threads. And these variables tend to be the ones that we need to track for the potential analysis anyway. So we'll restrict our attention to just those variables that have the same value across threads. To do this, we have to add to the pre and post conditions a set of variables that have the same value across threads. We'll restrict the potential function to only look at the state of these variables. We require that for all variables in the set, all threads have the same value. And under this assumption, we prove the same statement I motivated before, which is that the cost of evaluating a statement S is less than the difference in potential between the before and after states. This fact is the soundness theorem of the quantitative logic, and we've proven it in Conc. Again, I'll use if as an example. There are 4 rules. I'll just show 2. Like before, we carry through the knowledge that E is true when we analyze the then branch. In the else branch, you might think we would have P and not E as a precondition, but it's not quite that simple. We do require that the precondition of the else branch be implied by P and not E. We also require that the precondition is implied by the postcondition of the then branch, because remember, if the warp diverges, the if branch and the else branch might happen in sequence. We need enough starting potential to evaluate the condition, pay for the if statement and the possible divergence. We then take the remaining potential Q and thread it through the if branch and then through the else branch. Finally, when we evaluate the else branch, we take the variables that were uniform at the end of the if branch and subtract off the variables that were written to by S1, which we can determine syntactically. Because not all threads might have been executing S1, these variables that were written to by S1 might no longer be uniform. We do the same thing at the end for the variables that were written to by S2. That's the general rule for if, and it's always sound, but it would be pretty imprecise to use it in most cases, since it assumes that every condition diverges. If we can prove, on the other hand, that only one branch is taken, that is, all threads in a warp take the same branch, which we represent here with this condition E unif for uniform, then we have a more standard rule for if that essentially takes the maximum cost of the 2 branches and requiring that both branches have the same ending potential function. So just like the standard rule for if that I showed before, weakening lets us throw away some potential if one branch ends up with more. Let's take an example program that takes an array A and a matrix B and adds a pointwise to even rows of B and subtracts it pointwise from odd rows. We have 1 thread per column, and the code for each thread iterates over the rows. We first load the value of A for the column into shared memory, and then iterate over the rows 2 at a time, performing all of the additions and subtractions. For the purposes of this example, we'll assume that all costs other than memory reads and writes are 0. We'll start off with no information and some amount of potential. This potential has 2 components. One depends on the value of J, and one is constant. The actual amount will need to be inferred by solving constraints, but just for example purposes, I filled in what will turn out to be the correct amount. Also at the start, W, H, and J are all uniform across threads. So right away, we perform 1 global read of 4 sectors and 1 conflict-free shared write. So we use up the constant potential. We then set J equal to 0, so I can rewrite H as H minus J, not changing anything. This potential, L times H minus J over 2, is what we have initially, and it'll turn out to be the loop invariant for logic analysis, as we'll see in a minute. In the body of the loop, we perform a shared read and a global write, followed by another shared read and global write. Note that these global writes may write to 5 sectors instead of 4, since the first index may not be aligned to a sector boundary. We're left with potential L times H minus J minus 2 over 2. When we increment J by 2, though, this same potential becomes H minus J over 2 again. This is good because, as with the logical conditions of a standard for logic, we need to establish the loop invariant at the end of the loop. In this case, the loop invariant for the potential function is L times H minus J over 2. At the end, we know that J is greater than or equal to H, or more specifically, J equals H, so we have no potential left, meaning our initial guess at the potential was correct for this derivation. We've implemented the analysis as an end-to-end tool that infers cost bounds for essentially off-the-shelf CUDA kernels. We built this on top of the Absinthe static resource analysis tool, which is based on the quantitative program logic for C that I described earlier. But the extensions for CUDA are novel for this paper. The tool takes in a CUDA kernel and a resource metric. We perform an abstract interpretation to compute the logical conditions, including, for example, when a warp might diverge. We also convert the CUDA kernel into a lower level representation that can be read by Absinthe and is annotated with the cost of each operation. Then we hand this off to Absinthe, which generates constraints for the potential functions using the inference rules, and solves them using an LP solver. The constraint and LP generation portions are largely unchanged from Absinthe. Everything within that dotted box is contained in Absinthe already. The abstract interpretation part is new, but many of the details are standard, and I don't have time to talk about them here, so please see the paper for details. As I'll show toward the end of this talk, when I get to the evaluation, all of this works pretty well for predicting bottlenecks like divergence and bank conflicts. But if we want to predict something like actual execution time, we need a more detailed model. Such a model needs to reason about how GPUs schedule threads. Remember that threads are scheduled a warp at a time, but a GPU can generally execute multiple warps at a time. Each processor has more warps residing on it that can execute at a time because some will be waiting on things like memory. These warps are shown in the gray box over to the right. Each cycle, the processor picks as many ready warps as possible to execute and runs an instruction on them. Some of them might do something that blocks, like read memory, and others that are blocked might become unblocked. And this repeats basically forever. This execution model sounds a lot like the idealized model of how parallel programs execute on a CPU. So I'll use ideas from the theory of parallel scheduling. In that community, they represent the parallel structure of programs using a directed acyclic graph, or a DAG, where edges between nodes represent dependencies between computations. For CUDA, we have a very specific kind of DAG, many parallel threads that occasionally all sync at a specialized instruction called sync threads, which acts as a barrier for all threads in the block. For the purposes of this paper, we'll still only consider threads up to the level of blocks because composing blocks into a grid is more straightforward. In work from 2016, we extended the DAG model for operations like memory reads that incur latency. For such operations, we can add a weight to the outgoing edge representing the number of cycles of latency. A latency of 1 corresponds to a thread where the next instruction can be executed immediately, which reduces back to the standard meaning of a DAG edge, so we generally omit the ones. We define the work to be the total amount of computation time, not including latency, across all threads, and the span to be the time of the longest path, including latency. From these two quantities, the 2016 paper showed a bound on the running time. We can apply this result fairly directly to CUDA if we can calculate the work and span of a CUDA kernel. We extend the CUDA cost semantics to track a running total of work and span for each work. So the cost is now a pair of a work for each work and a span for each work. And the resource metric returns a pair of costs corresponding to the actual computation time of the operation and the latency that it incurs. The actual rules don't change too much. Usually we're just threading the totals through. But now we do something interesting on a sync operation, which corresponds to the sync threads function we saw earlier. On a sync, we take the maximum span across all of the warps and assign it to each span. This corresponds to all of the other warps waiting at that barrier for the last one in the block to finish. We also add the constant cost of syncing onto all warps with active threads. Just like before, we want a program logic that predicts cost statically. It turns out, though, that we don't need a new one. We can actually just run 2 copies of the old program logic with 2 different resource metrics, one that calculates work and the other that calculates latency or span. If we do that and we run the program, starting with all 0 costs, we want to predict the total work and span. Recall that the program logic was assuming just 1 work, so we need to compose the results accordingly to handle all of the warps in the block. The total work of the block is the sum of the work for all warps. It should be less than q minus q prime times the number of warps. The total span, on the other hand, is the max of the span for all warps, and it's just bounded by q minus q prime. It shouldn't depend on the number of warps. Returning now to our implementation of the resource analysis, we've evaluated the analysis tool on a number of benchmarks. Some of these are benchmarks that were distributed with the CUDA SDK, and some were written or modified by us. We used 4 resource metrics. 3 correspond to the bottlenecks we've been discussing throughout the talk: global memory sectors, shared bank conflicts, and divergent warps. And 1 is a metric we call steps that counts abstract evaluation steps. We ran the CUDA tool to get a bound for each metric on each kernel. To test the accuracy of the analysis, we also ran the kernel on a number of representative inputs on an actual GPU using a profiling tool distributed with CUDA. This can measure sectors accessed and bank conflicts. For most of the benchmarks, the performance is more or less independent of the actual input, aside from its size, but in cases where it mattered, we used worst-case inputs. It's important to note that the analysis is based on our model of CUDA execution, which is reflected in the cost semantics. So to tell whether any imprecisions in the CUDA analysis come from the analysis itself or from our model, we also ran each kernel with each resource metric on a custom-built simulator that essentially applies the evaluation rules of our cost semantics to get the cost that our cost semantics would predict. For the divergent warps and steps metrics, we can actually only compare the predictions of the CUDA tool with our simulation because the profiling tool distributed with CUDA doesn't capture relevant metrics. First, we compare our cost semantic model as implemented in the simulator to the actual profile values. Here, I'm showing the average absolute error of our simulation with respect to the actual value, averaged across all of the inputs we tested. As it turns out, in almost all cases, our model overestimates the actual cost. And where it underestimates, it does so only very slightly and only on some inputs, which is good because we want conservative sound over bounds. In a table, lower is better. And for example, an error of 0 indicates that our model was exactly precise, and an error of 1 indicates that our model gave double the correct value. In general, the model is quite close to actual executions in terms of the cost it gives. Most of these is within about 20–30%. Now I'll show the comparison between CUDA's prediction and the actual values. The results shown here are for a resource metric that counts the number of sectors read from or written to global memory. All their costs are 0. Here, we don't take the absolute value because in each of these cases, the prediction was actually an overestimate. On almost all of the benchmarks, the error is within about 30%, and the analysis time is under about a second or so. Larger and more complex kernels, like taking the Mandelbrot, calculating the Mandelbrot set, take longer to analyze, but still produce good results. In fact, note that several of these errors are actually the same as the error between the model and the actual value, meaning that all of the error here on this slide is due to imprecisions in our model and not in the analysis. To see what this looks like visually, here's a plot of the predicted worst case for the sectors metric on a matrix multiplication benchmark, together with the actual values for some concrete input sizes we tested. For simplicity, we just use square matrices and the x-axis as the dimension. The blue line here is our predicted number of sectors as a function of the dimension of the matrices, and the purple crosses are actual inputs we tested, the actual number of sectors written as profiled. Here's the same kind of plot for the add sub3 kernel that I used as an example earlier, which has two input size parameters, one for the width and the height of the matrix. The results for bank conflict are slightly more inconsistent. When a benchmark has no bank conflicts, our analysis is quite good at predicting that fact, but when there are some bank conflicts, our analysis often considerably overestimates the number of them. We can make this analysis more precise with a more complex abstraction domain that gives more information about array indices accessed. We already do quite well, though, with histogram, which has a complex worst-case behavior with respect to bank conflicts, and we predict it precisely. The histogram benchmark takes an array of n bytes and produces a histogram of the number of occurrences of each possible byte from 0 to 255. The 256 histogram bins are stored in shared memory. This generally doesn't result in many bank conflicts because in a random instance, bytes are fairly well distributed, and in a sample of 32 bytes handled by a warp, there aren't likely to be a lot of bank conflicts. This situation for a random instance is shown with the green x's in this chart. A worst case instance, though, results in considerably more bank conflicts, as shown by our predicted worst case and the purple x's, which are actual runs with worst case inputs. This also shows the importance of static analysis rather than just random testing. There's lots more work to be done here, especially when it comes to predicting more complex cost metrics like actual execution time. For one thing, this work only calculates abstract cost metrics, and for execution time, we need to have some way of relating these costs to real wall clock execution time. CUDA performance also depends on instruction level parallelism, which takes advantage of the lack of sequential dependencies between ostensibly sequential instructions within a thread. We also want to scale up to handling more advanced features of CUDA, as well as larger programs with many invocations of several kernels, such as large machine learning or computer vision benchmarks. In conclusion, we've been able to model and predict with good accuracy the performance impact of several common bottlenecks in CUDA kernels. I wasn't able to touch on everything in the paper in this talk, so please read the paper for more details. Thanks for listening, and I look forward to answering your questions in the live session.